Thank you for coming to another of our SISSA and IFPU gravity webinars. Today we are very happy to have with us Salvatore Vitale. Just to give the usual short summary on his bio, let me say that Salvatore got his PhD in the Pierre Marie Curie University in France, and then he was a postdoc in ChiEffective in Amsterdam and also in the MIT, where he is now an assistant professor. Salvatore is very well known for his work on data analysis of gravitational waves in order to start physics and astrophysics from there. And precisely that's what he's going to talk about today. So thank you very much, Salvatore, for coming, well, at least digitally to talk about this to us. And well, you can start.
Absolutely. Thank you, Mario, for the introduction, and thank you, everyone, for the invitation. I'm very happy to be there, even though only virtually. So let's see. First of all, I apologize for the very vague titles. This day, you never know what we are going to publish when in the LIGO collaboration. So it's good to have a generic title. So depending on what happens, you can, change a bit the topic. All right. I should also say, for those of you who care about this thing, that next week it's a NASA Black Hole Week. That's where I got this nice alien with the Hello Black Hole flag. I didn't make it myself, sadly. So it's going to be quite a lot of events, I think, if you're interested in these things. All right, so let's see. I will keep the introduction on the basics, existent but not too long, since I expect that most of you will be familiar with at least the basic principles. And so let me start with a quick introduction of the type of sources of gravitational wave that I will care about today specifically. This slide here, which hopefully is going through without too much buffering, is really representing the type of systems that we expect to be out there and that emit gravitational waves. So we divide typically them in persistent, which is the first column, and transient, which is the first column, and persistent, which is the second. Now on the transient, there is the one type which we have detected so far, which is the spiral merger and ring down of two compact binaries, for which I will use the acronym CBC later on. So you have probably all seen this video by the SXS collaboration. So everything we have detected and everything I'm going to talk about today lives in this category here. But there is more out there to be found. There is any violent explosion, like core collapse supernovae, so anything with a non-vanishing quadrupole moment, pretty much, a derivative. Then on the persistent column, there are axisymmetric neutron stars. As long as they're not perfectly spherical, they should emit monochromatic gravitational waves. We have not found them yet. And then finally, there is the stochastic background, which here it's shown as the surface of a lake on a rainy day. What this is meant to convey is that this is the sum of all the events which, taken one by one, are too weak to be resolved, but altogether may give a measurable signal. And we have also not found those yet. All right, so as I said, today I'm going to talk entirely about CBCs, so in spiral merger and ring downs. Let me first show you quickly where we are as a community. So as you know, LIGO and Virgo have taken data since 2015, with Virgo joining a bit later. And as of now, we have had 3 observing runs, the last of which roughly for 1 year and finished a year ago, pretty much. It was ended earlier because of COVID. There were 56 candidates event made public, which is 1 a week, which is, if you think about it, is pretty crazy that in 5 years we went from the first detection ever to 1 every week. Most of them were vanilla at this point, binary black holes. There have been a few interesting oddballs. And a few months ago, we put out, the LIGO collaboration put out catalog papers for DO3A observing run. I like this plot here on the left because it shows clearly the dramatic change of slope we had between O2 and O3. So in here you see on the x-axis the observing time in days. This is non-consecutive, of course. And on the y-axis, the cumulative number of detections that we have made. And the different colors give you the 3 different observing runs, where the third one was broken into bits. We have published the blue bit only. And you can see how something quite significant happened at the end of O2, which changes the slope. That thing is the implementation of quantum squeezing in the LIGO detectors, which really increases sensitivity. So right now we have on the order of 50 binaries, and there are maybe 20, 30 more which we have made public in real time, but we yet have to confirm with a publication as being, 5 sigma events kind of thing. So the point I want to make here is that we are really already in the regime of populations, right? We went very quickly from, this event is interesting and this event is interesting to have, these 20 events which can teach us something, or 50 events and hundreds very soon. Right, so with all these events and all these sources, what people like me, can do, and the reason why we care about is that, of course, we can use the signal and the shape of the signal as detected here at Earth to learn something about the source, right? And in particular, we can learn things like masses and spins of the two objects, tidal deformability. Like, I should update this slide. This was made before the PRL paper of last week. I say tidal deformability of neutron star, but there was an interesting PRL last week where people have shown that spinning black holes also have a non-zero love number, and have proven it. And sky position, distance, orientation, and so on and so forth. And with this information, taken both in an event-by-event basis and all together, you can address problems like formation and evolution of compact binaries, neutron star equation of state, cosmology, test of GR, search for dark matter, and EM emission, and whatever stimulates your fantasy. So there is really a lot of science that can be done. And of course, since I've been given 50 minutes instead of 50 days, I have to make choices. So the first choice is I will only take about black holes today. I will entirely skip neutron stars. And to be even more specific, I will only talk about black hole spins. Okay, so my talk is going to be focusing on spins, what we can learn from them, and a few other things. As a quick motivation as for why I personally care about black hole spins specifically, although it's not the only thing I do, is that measurement of black hole spins with gravitational wave is entirely orthogonal to what you can do with photons using X-ray binaries. And that matters because the measurements based on X-ray binaries may suffer from systematics due to the incredibly large amount of modeling that goes into it. They are also a good discriminant for black hole formation. So whether the spins are small or large or aligned with the orbit or not, you learn something. They can teach you something about supernovae because the spin angle are impacted by the details of supernova physics and explosion. They depend on binary evolution, things like common envelope. They give us access to the Kerr metric, can be used to search for axions, as I'm going to talk about later, and to test general relativity. And this is only a short version of a longer list. All right, so with this in mind, that's the rough outline of today's talk. I'm going to divide it roughly in two parts. The first one is going to focus about what we can learn from one gravitational wave signal, with also a small section on caveats, which I think it's good that people outside of the LIGO collaboration appreciate fully. And then I'm going to move to what can be learned from many gravitational wave signals. I'm going to focus on ultralight bosons if time allows, and I expect that it won't allow. I'm going to also talk about formation channel of black holes. I should also say that I'm perfectly happy for people to unmute themselves and just speak if you have questions, unless Rico and Mario want to moderate in a different way. All right. So let me start from the first part, which is going to focus on individual sources. Some of this will be introduction, which hopefully will be useful for those of you who don't think about compact binary every day. So let me start with the physical picture of what I have on mind. This is a typical source. I have two black holes. They have mass 1 and mass 2. Hopefully you can see my pointer. And I should say for later use that I'm going to use the index 1, as we do in the literature, to refer to the most massive of the two objects. And each black hole may have a spin whose magnitude is A1 and A2, and the spins might form an angle θ1 or θ2 with the orbit L. And the observer is looking at this object, at this binary, with an orbital inclination I or iota. Now, ideally, I would love to measure all of these parameters. I would love to tell you what the masses of the individual objects are, what the spins of the individual objects are, and so on and so forth. Realistically, that's hard. And it turns out that there are some combinations of these masses and spins that we can measure better than the individual parameters. For example, instead of measuring the component masses well, what we measure very precisely is the so-called chirp mass, this curly M here, which is a combination of the component masses and the total mass, pretty much. You probably have seen this already. And same goes for the spins. Instead of measuring very well the individual spins, we are pretty good at measuring this so-called ChiEffective, which is basically the mass-weighted combination of the spin projections along the orbital angular momentum. Here you see a vectorial representation of chi-f. Okay, so this we measure relatively well. And the other side of the coin is that we measure quite poorly typically this chi-p. P stands for precessing or perpendicular, which is the component of the spin along the orbital plane. I'm going to go back to that later on, which kind of sucks because chi-p is what would tell you something about misalignment and precession. All right, so keep this in mind. And of course, if you care about why it's easier to measure those than measure the individual masses, people like Enrico are much more qualified to tell you about that than me. But basically, at the zeroth order, that happens because if you develop the phase of the signal using the post-Newtonian theory, for example, power series of V over C, these terms are lower order corrections than the individual masses and spins, so we measure them better. It's as simple as that. All right. So what this implies is that if you look at a binary like this, here I'm showing the last 2 seconds of this is a simulation, of course, it's not a real event. And this is come from, if you want to have a look, especially if you're a student, to a recent review I wrote of the first 5 years of gravitational wave astronomy. And so here I'm showing the strain on the y-axis versus time. And we typically talk of a spiral very early on when the two objects are far away. Then as they emit gravitational wave and the orbit shrink, eventually they collide and we talk of merger and ring down. Now, morphologically speaking, if I look at this, from various features of the waveform, I can already guess properties of the source. For example, by looking at how long it is in the LIGO and Virgo band, I can tell something about the mass of the system at the zeroth order and the spins, in particular ChiEffective. By looking at the phasing evolution, so how f and f dot evolve, I can say something about the chirp mass, the mass of the spins, and the tides if they are there. The overall amplitude of the waveform tells me something in combination about how far the source is and what orbital inclination is. They are unfortunately badly degenerate. If there is amplitude modulation, like in this case, you can probably see it, I learned something about spin's angle. And the reason is that if there is misalignment between S and L, then of course you have orbital precession. So if you're looking at the system, you will see more or less, gravitational wave amplitude as a function of time. So that gives modulation. Finally, from the last few cycles after the merger ring down, we can learn something about the nature of the compact object. All right, so if you have paid attention here, in most cases, spins enter as, they're not the first item in my list, which means that they're not the easiest thing to measure. And this became quite apparent already before the first gravitational wave detection in 2015. So, already back then, I started looking at how well we can measure component spins, right, instead of these agglomerated quantities like ChiEffective. And the answer turned out to be not very well, right? And as I said, there are high order corrections. And if you look at the details of the phasing of the waveform, it also turns out that it's harder to measure spins when the two objects have roughly equal mass. It's harder when the spin magnitude is roughly the same, and it's worse for phase-on systems. These are systems where the binary, it's phasing you this way pretty much, which is most detections, unfortunately. Right, this point is made numerically by now all paper. Back then it was a status of the art. What I'm showing here, it's on the x-axis, the signal to noise ratio, SNR, of the detection. These are binary black hole. It's a very complicated plot, so I won't go through it in detail. I'm going to show a few highlights. The y-axis shows you the 1 sigma uncertainty on the measurement of the magnitude of the spin of the primary object. That is the most massive. Okay, so you have 5%, 10%, 30%. All these points are black holes binary where the primary is 10 solar masses, the secondary is 5 solar masses. You will notice these are quite lighter than what we are detecting these days. That's because back then we thought that these were going to be the typical binaries that we would detect. The primary spin is 0.9, so it's close to maximal care. The size of, sorry, the shape of the object tells you whether the secondary spin is 0.1 or 0.9 for square and circle. The color finally tells you what is the orbital orientation. 0, so blue, means face on, is shown here in this very small plot. So you're looking at the orbit from above. Pi/2, it's what we call edge on, so you're looking at the orbit from the edge. And you can notice that overall, the uncertainties are much smaller when you're looking at the system edge on, so close to the red, Pi/2. And if you're looking at system edge on and the spin are pretty large, then you can do measurements as well as 5 or 10% if the signal to noise ratio is pretty high. On the other end, if you're looking at system from face on, so if you're looking at the blue plots, at the blue points, the typical uncertainty, that's 1 sigma, okay, it's 20, 30%. If you convert 1 sigma to 90% credible interval, it means basically you're not doing really a measurement, you're getting your prior back. I'm gonna go back to this point later on. So this is a pretty grim picture, and it's also stimulated papers with pretty dramatic titles like the one you see here on the left, where people really started questioning about whether it was going to be possible to say something about the spin of individual objects from individual gravitational wave signals. There is more information from this plot, but since it will take 10 minutes by itself, I'm happy to go back to it later if people want. We consider other things like the orientation of the spins and so on and so forth. All right, the one thing I want to say, which is already hinted at here, it's easier to measure spins if you are living here, which means edge on. So you may tell me, that's great, and let's just wait until we get a signal which is edge on, and then we can measure black hole spins very well. Sadly, that is true, and this was already noticed by Apostolatos in 1994, that spin and precessional effects are larger when you are edge on. Unfortunately, gravitational wave emission, it's less efficient, and if you're looking at the system edge on, and is most efficient face on. And Bernie-Schutz did the math, and you can then realize that only 3% of the detectable systems will have an inclination higher than 80 degrees. You can convert this statement in a spin measurement kind of forecast, which I've done in this plot here. Here I'm showing for various black holes binaries. Different points are different mass and mass ratios. Again, it doesn't really matter to go into details for now. What you see in the x-axis is the orbital inclination. 0, it's face on. Pi/2 again is edge on, and pi, it's face away from you. And on the y-axis here you see now the 90%. So I switch from 1 sigma to 90% of the spin magnitude again. I'm using, I should say, is in the next slide, but it may be useful to specify it now. I'm using, of course, dimensionless spins. So the range is between 0, which is non-spin, to 1, which is maximally spinning. All right, if you focus on the systems for which there is some amount of precession, which are the blue and the red dots here, you will notice a clear trend with inclination, which was already hinted at from the previous plot. But here you can also get an idea of how much you can gain by looking at a system from edge on rather than face on. We're talking a factor of 2 or 3 improvements, right? In some cases, you don't win that much, like for this cluster of points here. These are points with a pretty much equal mass or aligned spins for which the effect of precession is not very prominent in the first place. But when there is precession to be seen, you see it much better if you are edge on. Again, sadly, we're going to see only 3% of the events here, and most of our detection will be here or here. And indeed, if you look at the LIGO catalog and Virgo catalog, that's where most of our signal live. That's why our system spin measurement typically are rather poor. You can show the same information in a slightly different way. Here I have 200 binary black holes with masses in the range 30-50. So now I'm getting a bit heavier. These are consistent with 15914. This is the x-axis is just an event ID. The green points here are the true values of the spin magnitude. The blue bullet and 90% are my measurement. Basically, this plot is making the point that I'm not really measuring spin magnitude, except maybe sometimes for very large spins. Likely, as I mentioned earlier, we can measure better this ChiEffective. So what I'm doing here in the bottom panel is that for the same 200 events I have here, I'm showing how well I can measure this spin projection along the L angular momentum. And you can see how indeed that's much better. Typical uncertainties are, 10% or something like that instead of being the whole range. Okay. Even though I'm not showing it in here, the same, the opposite is true rather for Chi-P. So that's the precessing degrees of freedom, which is not well constrained. The reason why it is so is because you need the logical end of many pieces to be true if you want to measure Chi-P well. You need large spins, they need to be misaligned with the orbit, and the inclination must be large. And making all of these things true, it's very hard, sadly. And indeed, if you look at the LIGO catalogs and Virgo catalogs, these projections that we made back then, a few years ago, they turned out to be true. This is a plot from the O2 catalog. I'm not showing the latest one because the plots are just too big to learn anything from it. They're very hard to read. And so you can see here posteriors, these are violin plot with the 90% uncertainty for ChiEffective. And indeed, you can see that they're measured rather well, while Chi-P on the right panel is measured very poorly. Here, the empty half of the violin shows the prior, the Bayesian prior. I'm going to go back to this point in a second. And the color side shows you the measurement. And the point is that they are the same. So you're not really learning a lot from the data about the precession spin. You are learning a lot about the aligned spin component. All right. The one thing I want to do next, having talked about how hard it is to make this measurement, is to actually go even a bit deeper and talk about some of the important caveats that are associated with making these measurements, which are not always fully appreciated unless you spend time thinking about it. So the point I want to make here is that what we typically report in LIGO Virgo paper, or I should be fair, of course, and a lot of you know that there have been black holes found outside of the LIGO Virgo collaboration by people in Princeton or in Max Planck and a few other places. But everyone uses eventually Bayesian analysis that looks in one slide like this. What we want and what we report in our papers, it's a measurement. That's a posterior distribution, is this object here, on your unknown parameters, theta, given some data and some model for your signal. Using Bayes' theorem, that is the product of a likelihood, which tells you how likely it was to get the data you had if you knew the parameters, the Bayesian prior on the parameter, and some evidence which we can treat from today as a normalization. Now, the important thing here is that the prior, it's partially subjective. The prior represents what you think you know about the signal parameter before you analyze the data, okay? And the likelihood depends on detail of the analysis, such as noise handling, waveform modeling, and so on and so forth. And there are quite a few things that can go wrong or must be dealt with extreme care, and are not always expressed in full details in papers. So there are many examples I could make of this. Probably the poster child is the events reported by my friends in Princeton. So hopefully you are aware of this, right? A year ago or so, a colleague in Princeton at reported the discovery of additional binary black holes in LIGO Virgo 1 or 2 data. What they did was pretty amazing. They wrote pretty much their own pipeline for searching, and they discovered a few other things, and they reported the estimates of the parameters. This is their money plot. On the x-axis, you see the total mass of the binary in the source in the spin in solar masses. On the y-axis, you see this effective spin. The blue contours are the LIGO Virgo events, and the yellow, green, and red are the ones they reported, which were new. The color represents the probability that they quote for each of their new events to be astrophysical, from 0.5 to 100%. Now, the thing to notice and that struck my attention when this paper came out on the archive is this source here, which has a very negative ChiEffective, and these sources, which are very positive ChiEffective. Contrast with the LIGO Virgo measurements, which are the blue points, which are, or rather areas, which, as you notice, are all scattered around zero, right? So this was a big deal when it came out. You know, they got the cover of PRD and the suggestion because exactly of the evidence for this highly spinning with positive ChiEffective binary black hole. So when I saw this, I asked a student of mine, of course, to run the parameter estimation algorithm that we use inside the LIGO collaboration and the Virgo collaboration on their reported event to see what we would get, right? And if we also would get a large and positive ChiEffective. So that was the beginning of a pretty extensive study that we did in collaboration actually with our friends in Princeton to understand what if we were going to get the same thing, if not, what was different, right? So we took a lot of things into consideration, from the Bayesian prior to the noise handling data and segments and whatever. I won't go in extreme detail. I'll tell you that everything can have an effect. But today I want to focus on the Bayesian prior here. So let me show you the main difference between what the Princeton paper has done and what the LIGO collaboration and Virgo collaboration do, right? So in here I'm showing on the left panel the Bayesian prior on ChiEffective. So that's what, again, this is the prior, that's what we think we know before we do the analysis. So we enforce this a priori. What LIGO and Virgo normally do is to assume a Bayesian prior on the spins, which is flat on the magnitude of the individual spins, right? Which is this absolute value of chi, so the orange curve here. If you convert this into the relative, the resulting prior on ChiEffective with the proper Jacobians and whatever, you get this peak distribution at zero. On the other end, what the Princeton people have done is to use a Bayesian prior, which is flat on ChiEffective, right? And the configuration A and B from the LBC differ in whether you are a waveform which has only a line spin or allows for precession. It doesn't really matter for today. Okay, so the question then we ask ourselves is, how solid are the results, in particular this very large spin they found, to this choice of prior? And the answer is not very much. This corner plot may be too small to read, so let me zoom on the ChiEffective part. In here, I'm showing the measurement using the settings that Princeton people have used, and indeed you see something that peaks at 0.9 pretty much, and is not inconsistent with being maximally care. And the green and orange here are the measurements you would obtain using the same setup as the LIGO and Virgo collaboration. And it still peaks at relatively high spins, but now you have developed this very large tail, which makes it not inconsistent without actually no ChiEffective, right? I'm happy to go back to this point later if people want, because of course, this has also an impact on things like masses, because mass and spins are correlated, right? All right, so this is again just one example of one example of the need of being careful when interpreting results from the literature, because sometimes there are these subtle effects which are not fully taken into account. And I should say again, there are multiple more examples. You can look a bunch of papers where I also involved for other events where we have shown similar features, right? And I should also say that this does not only pertain to spins. Priors are also important for things like distance and inclination. So if you care about things like Hubble constant measurements, which requires distance measurement, that also, oops, I think PowerPoint died, apologize. Let me restart it very quickly. That will also depend on the priors. Actually, while I restart this, let me see if people have questions now, so we can take advantage of the undesired pause. If not, I am actually already back.
I would have a naive question, if I may ask. So which should we?
Of course.
Yes, thanks. So what prior should we consider to be more correct naively? I mean, they impact the result, as you said, okay. But what is the better choice for them?
I understand the question. It's a very relevant question. So let me go back to it. By the way, I'm going to give another shot to PowerPoint. If it fails again, I have a PDF version of this, so I can quickly switch to PDF since I don't have animation. Right. So there is not a correct answer to that question, Sebastian. It really depends on what you are doing. Now, I can try to justify our choice, which is using something which is uniform in the component spin. My justification of that would be that that's the physical quantity that it's relevant for the, to describe the system, right? You are trying to measure and you are writing the problem as a function of the two individual spins, right? And if you assume you don't know anything about that, that's a reasonable prior to use. Now, their argument for using something which is flat in ChiEffective is that that's the parameter that you measure best. So they use a prior which is flat on that. I had a long discussion with my friends in Princeton. That makes me nervous because if you think about the masses, then the equivalent would be to use a prior which is not flat on the individual masses, but is flat on the chirp mass just because you measure that better, right? Which seems a bit harder to sell. But the truth, Sebastian, is that if your result depends this much on the prior, it means that it's not a good measurement in the first place. So you have to be really careful, right? I think that's really what I learned out of this. If your result moves by 5 sigma, or if you just change the prior, there is something, your likelihood is just not telling you very much. I'm happy to talk more about this, but
no, this was already
a lot of time thinking about. But since it's
Salvatore.
All right, since it's 38, somehow magically I'm gonna yes.
I have a question just so concerning the use of the flat prior on effective spin. Doesn't it result somehow on a weird prior for the mass ratio? Because you have the condition that the spin should always be within -1,1.
Yes, yeah, that I don't know if I would call that weird, but it does indeed impose a prior on the spin, on the mass ratio. I don't have the plot here with me, so I cannot show that. But yeah, that correlations result on a prior on the mass ratio, which is not necessarily uniform, indeed. All right, I should probably move on if I want to finish at 9. I'm happy, of course, to stay longer if there are questions. All right, so the last thing I want to say about individual events before I move on to the population is something pretty actually fun that we have done recently with a student of mine here at MIT. And so, we were bugged by the fact that LIGO and Virgo kept publishing paper and people reading it as LIGO and Virgo are detecting black hole spins which are small, right? And so let me tell you where I'm going with this. If you read a LIGO and Virgo paper, you see plots like this where we report the probability distribution, so the posterior, of the individual spins. So this plot works like this. The darkness gives you the posterior probability, so darker means more likely. The left side is for the primary object, which is the most massive. The right side is the lightest object. The radial direction gives you the spin magnitude from 0 to 1. The angle gives you the spin tilt angle, so the misalignment with the orbital angular momentum. So, for example, this event here, which is 1226, if you look at this, you probably conclude that you cannot say anything about the secondary spin. And for the primary, you can say that maybe it's 0.4 in magnitude, and I cannot really tell you very much about the alignment. It could be a bit everywhere, right? So what we realize, and this happens over and over for all of our events pretty much, there is a lot of support with the spin being 0. So what we realized pretty much as a side project of something else we were doing is that you can ask the data a different question. Instead of asking the LIGO Virgo data, what is the spin of the most and the least massive object on the binary, you can ask the question, what is the spin of the most spinning object on the data, okay? Which is a very different question conceptually, right? And mathematically, that basically eventually boils down to the fact that when systems are close to equal mass, sorting your events, but your binary by mass doesn't really make sense anymore. It basically breaks down, right? And if you do a spin sorting instead, and you ask yourself that question, for example, for this event, you discover that the most spinning object in the binary for 15, 12, 26 actually has a lot of support for being spinning and maximally care, while the least spinning object in the binary has, support for being spinning from 0 to 0.3 or 0.4 or something like that. And this propagates, if you want, at the population level. I won't go into detail now for time. We have this paper which is on press with PRL, and it's just fun. I invite you to read, because it's just a slightly different way of thinking about our detection and what it is that we are measuring. All right, in the last 15 minutes or so.
I'm sorry.
Go ahead, Enrico.
The most massive, I didn't understand. The least massive is the most spinning, or?
No. We just, so when we do this, the thing on the left, we don't care about the masses anymore.
I know,
okay?
but
so I'm not trying to call my...
Yeah, but if I compare the left to the right, if I compare the left plot to the right plot, it seems like the one that's spinning with almost extremal spin is M2, because the M1 doesn't have support near. Am I reading this wrong?
No. Okay, so you cannot compare. No, you cannot compare these plots this way, right? So what I'm showing here is not S1 and S2 anymore, is what we call SA and SB. So this posterior, pretty much, contains contribution from what in this other plot would be in possibly in both sides, right? So what you do, if you think about the NC as a cloud of point, for each point, instead of looking at this and say, okay, then the spin of M1 is this and the spin of M2 is this, I look at the spins and I say, basically I check what is the largest value of the spin, no matter where masses come from, pretty much, and I put it on the left panel in here, if it makes sense. Yeah, so I should have said this more clearly, sorry. This is not just a mapping of these points in here. It's both halves can contribute to both halves of this side. It's basically an order ranking statistics, pretty much. Okay, I hope you will discount me the question time, because I will clearly run a bit late. So we'll put questions in the way, which is great. All right, so let me move on to from single events and all the caveats related to it to what we can learn from a population of binary black holes. Okay, the example I will give is something that I had a lot of fun playing with pretty recently, together with a student here and some friends, which is searching for ultralight bosons. I am quite confident that in the audience there are experts of this on the theory side, which know way more than me. So I will be just very quick and give you my kind of cartoon interpretation of what's happening, and mostly for students out there. All right, so the idea here is that we can use black hole spin measurements to probe and search for ultralight bosons with masses, you know, pretty much of the order of 10 to the minus 11, 12, 13 electron volt. Now, my one-line motivation and explanation of ultralight bosons is that they are pretty much, they can be a lot of things. They could be the QCD axion that would solve the strong CP problem and the magnetic dipole. They could arise in string theory. Actually, they do arise quite naturally. They could be potential dark matter, and they can also can be anything really. They could be scalar, vector, tensor bosons. Or for today, everything I'm gonna talk about will focus only on scalar bosons, because that's where the theory is best understood for what I want to do. And I will also neglect self-interaction, which basically makes my results valid for high, pretty large decay constant, right, of the order of 10 to the 15 GeV and larger. So that should be valid certainly for example, for the QCD axion, for which we expect FA to be 10 to the 20 GeV or something like that. All right, why black holes tell you anything about these ultralight particles? Well, they do because of something called the black hole superradiance. Again, this is a very simple pictorial version of what's happening. The idea is that even classically, you can extract energy from a black hole through the Penrose process. For a particle, the idea is that if you throw a particle the right way and it breaks in the ergo region, a part of it can come down with more energy than what you put in, pretty much. For waves, the same thing happens. You can think about the amplitude of the wave being amplified. Okay, now, of course, if the particle goes to infinity, then nothing special happens. But if for whatever reason the particle or wave, once it's scattered, doesn't go to infinity, but comes back to the black hole, this process can happen over and over. You can suck energy and angular momentum from the black hole in a pretty dramatic way. This is what's called superradiance. Now, for the boson, what provides this mirror around the black hole that makes it bounce back is basically its own mass. It's, it's just the potential. Right, so you do the math, and people have done it extensively. There are great reviews. What you discover is you have an exponential growth on the number of these bosons that just come off the vacuum. So after a while, you can develop a huge, pretty much, cloud of bosons around the black hole at pretty large distances. These are much larger than the Schwarzschild radius. Now, mathematically, what you do, at least for the boson version, the scalar version, is to solve a Klein-Gordon equation in curved background, and you have hydrogen can happen efficiently only if, as long as the angular momentum of the black hole is larger than the angular momentum of the cloud, because the cloud needs to suck in pretty much black hole angular momentum. Another condition is that there must be a good matching between the two objects. So mathematically, you want that the Compton wavelength of the boson, it must be comparable to the pretty much the Schwarzschild radius or whatever, the typical size of the black hole, which is this alpha parameter. You want this to be smaller of the order of 1. And so that's one condition. That means that for any given black hole, there is, with some mass, there is a certain range of boson masses that could be excited. And the other condition, as I mentioned, is that you want the spin of the black hole to be larger than the angular momentum of the cloud. If those conditions are verified, then the cloud extracts angular momentum from the black hole until this condition is not met anymore. So until the black hole spun down enough that you reached some critical value. Okay, so this is the link between black hole and axions. Going a bit deeper, there are actually 2 observational signatures. One, it's from the cloud itself. What you can show, there is groundbreaking work by Mina Arvinataki and others. You can show that the cloud itself would emit gravitational wave, which are nearly monochromatic, but unfortunately, those are not very strong. So you could not detect those unless they are pretty much in the galaxy or very nearby. The other idea instead is using the spin of the black hole, right? As I said, if you have the cloud you can characterize it as a pretty much an hydrogen atom, so you can assign L and M quantum number, and you can show that for any given L and M, there is this critical black hole spin of the black hole after which superradiance stops. I'm going to show this with a plot in a second, so it will be more clear. We know how this depends on various quantities, so you can do at least a back of the envelope estimation of how long it takes for this cloud to steal the black hole spin. And it's actually pretty fast. If you take a black hole of 30 solar mass and an axion of 10 to the minus 12, the instability time scale, how this thing is called, for the main quantum mode can take as little as years. For the higher orders, kilo years or mega years. So that's a pretty fast process, all right? And what this implies is that if bosons exist, black hole of appropriate mass must have small spins. Why? Because the cloud will have reduced their spin until they meet the critical condition. Let me show you this with a plot, okay, which makes it much more visible. Here I have a 45 solar mass black hole, and I'm assuming that it starts its life from here with a spin of 0.8 something. Now that spin is below the critical spin for the L equal 1 cloud, so the cloud is never excited, but it's above the critical spin for the L equal 2 mode, so that cloud forms very quickly in 1 kilo year and reduces the black hole spin until it's here. The black hole may be parked here for a while, depending on how quickly the cloud depletes, and you may have the formation of the next mode because the critical spin of that mode is even lower. So in another 100 million year, the black hole spin will be reduced even further. So if you detect your black hole, then and you can measure its spin when it's pretty old, you will find that the black hole is spinning pretty slowly, right? So if you convert this to a population statement, what this tells you is that if, for example, that of course is a cartoon picture, if when the black hole form, and I stress here the word formation, okay, when they are born, they have, say, uniform masses in the x-axis and spin on the y-axis. If bosons exist, what they will do, and here I'm using 10 to the minus 12 EV, and I'm waiting for 10 million years, what they will do is that they will spin down all of the black holes in the gray region through superradiance until they bring them along the critical path, pretty much. That is a combination of L equal 1 and 2 and 3 in this case. The exact detail depends on how old the black holes are. So the idea here is that instead of using a black hole at a time, if you use the whole population, you can try to look for either black holes which are too spinning to be consistent with the existence of a boson, so black holes in the forbidden region, which is the gray one here, or try to pretty much see if the black hole spin are along this critical pattern that would tell you that bosons do exist and infer their masses. All right, I hope this makes sense. So this idea has been already used at least for black hole in X-ray binaries, and people have made projections for LISA black holes and for future and LIGO black holes. There is a nice paper by Richard here. What we have done instead here is to try to make this in a sophisticated way with the gravitational wave detected by LIGO and Virgo. Now, why do I say that it needs to be sophisticated? Because there is an important caveat here. What LIGO and Virgo measure is this process, right? We have two black holes that form, then say that one of them is highly spinning, form a cloud of axion, which spins it down, then forms the next order cloud, which spins it even further down, then the cloud is depleted and the black hole merge here. What LIGO and Virgo tell you is the spin of the black hole here when they merge. But what matters is what spins the black hole had when they formed. So if you want to do this properly, you need to, if you want, rewind this process, okay? Because what I'm telling you is the following. LIGO and Virgo are measuring black holes which have small spins. So does this mean that we have found axions? Well, not really, right? Because the LIGO and Virgo black hole might have small spins, either because axions exist and they have spun them down, or because they were born with small spins to start with, right? And these two situations are partially degenerate with one another. So just making a plot like this doesn't really tell you very much, because this is showing the black hole spin when they merged, all right? So with my student Ken, we put together a method which does, the quotation mark, the right thing, which is using hierarchical Bayesian analysis, where you simultaneously, and this is crashed again, apologize, it's very annoying. Let me restart in the PDF version of it, where we see. Sorry.
Let me use the crash to say that you have around 5 minutes.
Yeah, go ahead. I what?
You have around 5 minutes left.
Okay, absolutely. That should be enough. And I have PowerPoint here. Apologize about this. I didn't do it when I tried this. I even removed a bunch of slides to make it fast. Okay, I am in full mode on PDF now, so that this cannot fail. That means I will miss a bunch of things like keeping track of time, but hopefully it's still a win overall. Okay, I'm back. Let me go back to the screen share again. All right, there we are. PDF, Acrobat, there it is. All right, hopefully this still works now. Okay, so now everything is on the way. Let me try to move.
Yes, we can see it.
Very good. So fantastic. So what we have done is to simultaneously account for a possible boson mass and for the astrophysical distribution of the spins of the black hole when they formed, by properly time evolving them from formation to merger. Okay, so what you can do with this method is that if bosons exist, you can measure their mass. If they don't exist, you can put a limit, you can do model selections, and so on and so forth. Here I'm only showing you, this is a simulation from this paper, basically how this looks like for parameter estimation. Here, for example, we are simulating a universe where bosons do exist and they have a mass of 10 to the minus 12 eV. The blue lines are the measurements using a model that does allow for the existence of a boson in a range between 10 to the minus 11 and 10 to the minus 13. So we do not assume that we know the true value, of course. And while also measure for the spin distribution of formation, which is a beta distribution represented by these two parameters, alpha and beta. For today, it doesn't really matter. I'm just showing them to tell you that we are also accounting for the spin. And indeed, you can see that you can, if your model does everything carefully, you can recover the right value of the boson spin, of the boson mass. Interestingly, there is a second peak here. This comes from the L = 3 mode. Some degeneracy there. It's pretty interesting. It goes away if you have more sources. The other thing I want to show you, which is because it's fun, is the orange thing. The orange curve, it's a model where you do not allow for the bosons to exist. That's basically what you would run in the LIGO Virgo collaboration. If you do that, the nice thing that you see here is that you get the spin wrong, because your model will you will measure the spin at merger, and because it doesn't know about the bosons, it will say that the spin of formations must be the same as they were when they merged, while in reality they wouldn't, which is a lot of fun. Anyhow, I'm happy to talk more about this, but probably given the timeline, what's more interesting for people here is an actual constraint that we have obtained from the latest data from O3A. So that's a paper we have impressed with PRL. It will appear on Wednesday next week. So what we have done is that we have applied the method I just described to the latest LIGO Virgo catalog. And now, if I show you a mass spin plot, and they focus only on 2 sources of the 50 that we have detected, you will see that those 2 are pretty interesting. Here you see the phone numbers is 190412 in green and 190517 in red. These are 2 black holes whose primary mass it's around 30, 40 solar mass. And here for reference, I am showing also as a dashed and solid line in black, a critical spin plane for a boson of 10 to the minus 12 and 2 10 to the minus 13 EV. If you remember what I told you before, if a boson of this mass exists, black holes should not have spin in the gray areas. So what this tells you is that, for example, 190517, which is the red one, is clearly inconsistent with the existence of a boson of 2 10 to the minus 13 EV, and is marginally inconsistent with the existence of a boson of 10 to the minus 12, because if bosons existed, this red thing should have been below, under this the shaded area. The 190412, it's a bit more nuanced. It could be consistent with 10 to the minus 12 and is marginally consistent with 10 to the minus 13. Now, we don't do, of course, that analysis looking at a plot. We have a full posterior, which is the full Bayesian machinery, which is shown here. Here on the x-axis, I have the log 10 of the boson mass, so 10 to the minus 12, it's here. On the y-axis, I have my measurement for the boson mass using all of the 50 plus LIGO Virgo black holes. Now, the blue line is my measurement using the whole set of detection. The dashed horizontal line is the prior, which in this case was uniform in log. What you can see is that the posterior has a pretty significant dip in the gray region. You can do the math, and what we found is that there is less than 0.1% posterior support for bosons in the mass range, which is 1.3 up to 2.7 10 to the minus 13 EV, right? We have also checked that this constraint actually is mostly driven by these two highly spinning black holes. By repeating the analysis, by removing from the analysis first only one of them and then both of them, that's purple and orange. And when we do that, indeed, that significance goes away. I should also say that here, some of you may be interested in this peak here, which seems or may seem to suggest that there is some support for bosons at 10 to the minus 12. There is more details on the paper. It turns out that that's actually not statistically significant if you do model selection, for example. All right. As I predicted, there is no time for any of this. So let me move to the conclusions, which I'm going to leave down here for you to read. And maybe as a very quick summary, I should say that, you know, what I talked about was really born out of 50 sources. And already with those, we start addressing some pretty interesting questions in physics and astrophysics. And now, to give you a scale, when LIGO and Virgo restart in a year or so, we will have of the order of 100 labs clear per year, way more if you're willing to use marginal sources. So things will get even better very, very soon. All right, I'll stop here and thank you very much for listening. Sorry for the technological issues.
Thank you very much for your talk. It was very interesting. Now we'll have some time for questions. I see that Nicola has raised hand, so go ahead.
Yes.
Yeah.
Thanks, Salvatore, for the very nice talk. It was really interesting. And I have a question about the last plot you were showing. So about the last two.
Yeah, let me go back.
Plots. So this, yeah, if you can go back.
Yeah. This one or the one even before?
No, the one even before yes, this one here. So you say that by excluding these two events here, you have that there is no inconsistency of any mass for the boson with the data, right? So it is just the presence of these two events. Okay. My question is, how do you know the age of the black holes in these two events so that you can say that they have been there enough to...
Thank you.
Yes.
I understand your question. Yeah, thank you. And this, of course, it's a good question.
Yeah.
We have... Yeah, I understand. So we do have, of course, discussion on this on the paper, which I didn't go through in detail. But let me expand on this now, because of course it's a very relevant point. So what basically is being said here is that earlier I mentioned that it takes some time for superradiance to kick in. So how do I know that my black holes are not, too young to have developed superradiance? Right. So the way we answer that question is by pretty much relying on numerical simulation and population synthesis codes that evolve black holes, right? So if you do that, what you discover is that the typical lower time scale for black holes to merge, well, time delay from formation to merger, pretty much in galactic fields and in dynamical environments such as a globular cluster, it's of the order of what I have here, pretty much 10 mega years, right? That's again is the lower end. Typical time scale are actually larger than this, which will give even more time for superradiance to happen. Now, of course, if you compare 10 mega years with this time scale, of course, that means that you have enough time to develop at least the first two modes, which actually are the ones that contribute to most of the spin down. Now, a counter argument to that, which I want to address, is that you may tell me, but what if these black holes were like born in a very dynamical environment, like an AGN disk, and pretty much they merged quite quickly right after they were born, right? I cannot exclude that, can I? So the truth is that you can't, but you can use you can make an argument based on rates, and it goes as follows. The channels that could possibly create binary black holes with high eccentricity, which is what needed for them to merge very quickly, right? So that you don't have enough time, are also not the channel that are expected to contribute most significantly to the overall detection rate of LIGO and Virgo, right? So I cannot tell you that for certain, these two events have not formed and merged after 10 minutes, right? But the probability of that happening, it's very low. To be, though, very open-minded, in the paper, we have repeated our inference by lowering our minimum time scale for merger from 10 mega year to 10,000 years. Okay, that's much smaller now, and is more consistent, if you want, with incredibly eccentric mergers. And what we discover if we do that is that the gray error, the gray band where this posterior is very small, does shrink as you would expect. It doesn't disappear. It shrinks by a factor of 2 or something like that. So indeed, your point is well taken, and we are aware of this. And since you mentioned caveats, there are other caveats I should mention. For example, another one, which is probably very close to the art of people like Enrico. It's what about the environment? What if black holes have a disk and the disk spin up the black hole, right? Is it possible that these two black holes have a larger spin, not because the boson does not exist, but because the boson did spin them down, but then the disk spin them back up by accreting angular momentum? Again, that's theoretically possible, but if you do the math, which again, we present some justification on the paper, you discover that for black holes of this mass, they would have had to accrete at more than Eddington, which is, where radiation pressure balance gravity, for millions of years to pretty much compensate the effect of spin down from the boson. So if you compare the time scale, the boson is so much faster than the accretion that you can pretty much say that that's not a problem, at least for LIGO Virgo black hole. Anyhow, I'll stop here. There are many more caveats, and I am aware of those, so we do address as many as we can in the paper. But yeah, that's what I can say. I hope that at least partially addressed the question
clear.
also. And trying.
Thank you very much.
Okay.
Also, no problem. I'm trying to find the participant list again while you go to the next question.
Yeah, there are a few raised hands. I don't know if we will have time
right,
for all of them, but okay, Eduardo.
You are in charge of this, so.
Yes, I mean, I think they are ordered by who raised it first. So, Eduardo.
Yes. Thank you for this very nice, very clear seminar. At the beginning, you mentioned the fact that chi-p is difficult to measure, but in the next observing run, with an improved Virgo and also with the addition of Kagra, we should be able to have some information about the wave polarization. Do you think that this is going to help in the determination of chi-p?
Thank you for the question. By the way, I did not purposely stop sharing the screen. I'm just trying to get it back because I couldn't see people's faces anymore and it was a bit annoying. All right, so my answer is no. I'm gonna tell you why now, pretty much. So the reason why I think that one, I mean, it will get a bit better, but it will not get significantly better. And the reason for that is what I mentioned pretty much here, right? So let's see, let me start from this slide. If you want to measure precession, which is what chi-p is about, what you need to do is to see the system precess. And to see that, the easiest way is to see that the system is doing this, which means measuring an amplitude modulation and measuring pretty much the fact that L is precessing around J. Now, if you think about it, doing this, and if you think about this as a plate, since probably there is just about after lunchtime, it's much easier to see a plate wobble if you're looking at the plate this way, because then every small change is very visible on your line of sight than if you're looking at the system this way, right? So what this implies is basically what was shown here, is that to measure the effect of spin precession is not enough to have more polarization content, like it would be the case for distance, for example. That helps. But you also have to be able to see the system from close to a John, because that's when the spin effect is more visible in the first place, right? And so the limiting factor then, Eduardo, is not how many detectors we have, but it's more what's written here. The fact that detectable systems are typically with very low inclination, okay? So that won't improve by adding Virgo and Kagra and so on and so forth. The only way you can improve this is by building detectors which are a factor of 10 more sensitive, what we call the next generation of detectors, such as the Einstein telescope in Italy or in Europe, and the Cosmic Explorer here in the United States that I'm working on. If you have a detector which is much more sensitive, so no LIGO or Virgo, then you can show mathematically, I have a paper on this I can send if you're interested, that in that case, the typical event will be a John, and then you will be able to measure spin precession incredibly accurately for basically all of your events. But in the next few years, I do not see chi-p to be well measured in general. There will be a few events for which you'll measure it very well, maybe because the inclination is on the high side. But even with Virgo and Kagra, I think your typical event will look like, I don't know what's happening here, will look like what I showed earlier here, something which is not extremely informative, sadly.
Thank you for the very clear answer. I'll post my email address so that you can send me the paper you promised. Thank you very much.
Absolutely. Absolutely. Thank you.
Okay, I think, well, we have 3 questions. If you're okay, we can just go over them and then finish. Alexandre?
I have no problem.
Okay.
Yes, thank you. So yeah, thank you very much for the very nice talk. And I have a question in the same spirit of Nicola's one. So because do we expect in fact that there should be a cloud around every black hole? So even, I mean, assuming that they are old enough that superradiance would have acted, but do we expect every black hole to be surrounded by a cloud?
So the answer is no, because let me see why. So the reason why is because of this. So suppose that these bosons exist, right, and they have some value of mass, which is called mu here. Now, not all of the black holes will have a cloud of those around, because for the superradiance to be efficient, you need this condition to be met, right? So what this means is that if you fix the mass of the bosons in the universe, that tells you that only some black holes of masses such that this condition is verified will be able to trigger pretty much a resonance. The others won't, okay? So even if bosons exist, only some black holes will be affected, not all of them, right? And this is why all of these quantities do depend on the black hole mass, pretty much. Now, this conditions is not a very strict equality. Superradiance will still up within some bounds. It will just be less efficient, so it will take more time for it to develop, and the energy will be radiated less efficiently, and so on and so forth. That's what motivates in our analysis, for example, the choice of our prior. I said that we use priors between 10 to the minus 11 actually outside of here and 10 to the minus 13 electron volt. Why have we picked this? We have picked this because we know that LIGO and Virgo can measure black holes with mass between, say, 5 and 100. And so if you ask yourself what mass of bosons can trigger the resonance with this type of black holes, you obtain bosons of 10 to the minus 11 up to 10 to the minus, or down to 10 to the minus 13. If you look at LISA's black hole, which are much heavier, right, then you, or can be much heavier, I should say, then you will look for lighter boson masses and so on and so forth. Hope that answers the question.
Yes, very clear. Thank you very much.
Okay, and the final question is from Enrico.
Well, it's a quick one. It's actually more of a comment. So you mentioned in the beginning that you neglect the self-interaction of the scalar field, but that won't have an effect on the formation of the cloud and the spin down of the black hole, right? It will have an effect on what the cloud decays into, whether it's gravitational waves or scalar waves, right? So I think you're qualitatively, at least here, because I'm asking this question, and this is the part of the comment that I have, is that these masses, if you assume that there is no self-coupling for the scalar field, these masses are already excluded from the stochastic background, right? Because essentially the cloud decays into gravitational waves, and that you can exclude. Right. With some caveats on the population, astrophysical population, you can exclude from the stochastic background, from the upper limits from the LIGO.
So my comment, Enrico, again, of course, I'm not a theorist working on axioms, but my understanding of this, chatting with people like Masha and Mina, is that if bosons, if there were self-interaction, of course, as you said, it would affect the way the cloud decays. But I think the point is that if the self-interaction is very high, then the cloud may decay as fast as what is being formed. So that would affect the time scales pretty much, and how much spin you can affect. I see that Richard is on the audience, and because he is the person who wrote this massive thing here, it should be the one commenting because he will know way more. Hi, Richard.
Yes, I was going to comment on that. So, yeah, so self-interaction can slow down the process, and essentially the reason is because, well, if the self-interaction are big enough, you can excite, because you have, you have couplings like 5 to the third, for example. You can excite modes that are not superradiant. So those decay to the black hole and make the black hole spin up if you want. And so you can have a process where you slowly extracting because of the superradiant modes, but because the self-interaction excites a non-superradiant modes, this puts spin back to the black hole and can slow down the process quite significantly. So in this recent paper by Masha actually does that quite in detail. And
this one.
I see.
Yeah,
You need a large.
Yeah, absolutely. Thank you, Richard.
Yeah, I mean, there was basically there will always be a sufficiently large self-interaction for which you can almost shut down the process.
I see. Okay.
I think I trust my student Ken on this. I think he did the math, and given our black hole mass, we should be safe at 10 to the 15 GeV, which is well below, for example, the axion, the QCD axion. So at least for the QCD axion, this approximation should work fine. And yeah, Enrico, your point about complementary constraints existing from the stochastic, of course, are well taken. And I am of the school that having complementary measurements is always better because
I was trying to
you never know how
point, actually. The
modeling things.
I was trying to make the opposite point, that this is less model dependent in the sense that you assume less about, you just need the formation, the spin down, the formation of the cloud. You don't have to assume anything on about what the cloud decays into. So I don't know. Yeah, so maybe
I see what you mean. Yeah.
Because that's why I thought it would apply, because the typical objection to the stochastic background bounds on superradiance is that the cloud could decay into, say, scalar waves, which we wouldn't detect because they're coupled very weakly to the detector, and so this bound evades that. That's why I thought of the self-coupling, because I thought in the presence of a, well, now I realize not too large self-coupling, what I would expect is that the cloud would decay both in gravitational waves and scalar waves, as a result of which the bounds from the stochastic background would become weaker. I don't know if I'm explaining myself. I'm happy to talk later about this.
Yeah, no, I think I understood what you mean. All right. Okay. Thank you, Richard, by the way.
Yeah, no problem. Yeah. Thank you for the talk.
I had a lot of fun. I had a lot of fun reading your Bible here.
Yeah, well, a lot of fun writing it also, I guess, but a lot of work.
Yeah, can imagine.
Okay, so if that's all, let me thank you again for your talk, Salvatore.